Colton and I decided to do number 16, and part A asks, a proton moves in a magnetic field at a moment in time. The velocity of the proton and the direction of the magnetic field are shown. The speed of the proton is 4 times 10 to the 5th meters per second, and the magnetic field strength is 0.2 Teslas. What is the magnitude and direction of the magnetic force that the field exerts on the proton? All you need to know for this problem is that force equals QV cross B. So first you take your right hand and you sweep V to B, and the force is into the page because your thumb is pointing that way. Next, you just plug in the values that are given. So we were given velocity equals 4 times 10 to the 5th, and the magnetic field equals 0.2 Teslas. So we plugged in the charge of a proton, the velocity, the magnetic field, and then we included the angle because it wasn't perpendicular. And then that's our answer.
Question 16b asks, a particle has the trajectory shown in a uniform magnetic field directed into the page. Is the charge positive, negative, or neutral? We determined that since the trajectory is linear and there's no acceleration, then there is no force being exerted upon the particle, which means the charge of the particle has to be neutral.
So we're still on number 16. Part C. This question says, an electron has a constant speed of 6 times 10 to the 6th meters per second in the circular trajectory shown in a uniform magnetic field. What is the direction and magnitude of the magnetic field? So you do this. Okay, so the first thing that you start off with is acceleration equals v squared over r. And for the v, you plug in your given 6 times 10 to the 6th. And for the r, we change 3 millimeters to 0.003 meters. Then once you get your acceleration value, you plug that into F equals ma. M is the mass of an electron, and then A is what we found to solve for above. Then once we get F, we can plug that into the equation F equals QV cross B. And then we just rearrange the equations so that we're solving for magnetic field, like what we were asked for. Plugged in our force from above, plugged in the charge of an electron, we plugged in the given velocity, and then we got 0.011, and then we got the direction is out of the page, because if you do the right hand rule. And we're back with the right hand rule, everyone. So the way you do it is you have your force is your thumb, your V is your pointer finger, and then B, the magnetic field, is your middle finger. So you line up your pointer finger with the V in the picture, and then your force is pointing toward the center of the circle. So then you can see that your middle finger is pointing into the page. And then the reason we got out of the page as the direction is because it's an electron. So it's just a rule that you flip it because it's QV cross B. So out of the page.
For part D, an electron moves to the right in a straight line with a constant velocity. There is a uniform electric field directed upward with a magnitude of 3 times 10 to the 5th volts per meter. If the electron's speed is 6 times 10 to the 6th meters per second, what is the magnitude and direction of the magnetic field?
So here we can see the trajectory of the electron to the right and the upwards facing electric field. And we use the two identities F equals QE, or force is equal to the charge times the magnitude of the electric field, as well as F equals QV cross B, or force is equal to the charge times the velocity vector cross the magnetic field vector, in order to say that QE equals QV cross B. And we canceled out the charge, therefore the fact that it's an electron is irrelevant, and we rewrote it as the magnetic field is equal to the electric field over the velocity, and we plugged in our values for the electric field and the velocity and found our magnetic field to be 0.05 Teslas.